Joao Costa Freire. I'm professor at Instituto Superior Técnico of Technical University of Lisbon, Portugal, and today I'm presenting here the results obtained by the Microwave Electronics Research Group of Instituto of Telecommunications of Portugal. It is a private institute, but one of our participants is the Technical University of Lisbon, IST. And I will present the results on designing monolithic amplifiers at 30 GHz using low-cost silicon germanium technologies that are optimized for working at lower frequencies, usually up to 10 GHz. Well, the motivation for this work was since the silicon germanium technologies design libraries available as no sufficient accurate models of active and passive devices to allow a first-run design of RF front ends for frequencies up to at least 30 GHz, systems that are used presently in future telecom services like VSAT and LMDS, and we intended to use these technologies. We need to increase the know-how to create efficient tools for a first run realization of these microwave and millimeter wave circuits with multi-functions, to have one chip transceiver using low-cost CMOS compatible technologies. Well, so we have the presentation divided in 5 parts. Firstly, I will start analyzing interconnection structures, namely the pads and the connection lines between the elements of the circuit, and I will show that they are very important in millimeter waves. After, I will present a study of the available spiral inductors models in the foundry libraries, and because they are the most difficult passive devices to model, and we will design and modeling a new spiral inductor with series resonant frequencies higher than 45 GHz. Then I will present 2 types of amplifiers. One is a simple wideband amplifier without any inductors, and after a low noise amplifier within spiral inductors to have a good compromise between input matching and low noise. Finally, I will present the conclusion showing the possible performance of these technologies up to the millimeter wave band, and what are the improvements that we should make on the models available in the foundry libraries to have a first run good results. So starting with the test structures, I present in this slide the layout of a spiral inductor, the only one available on the foundry. Well, in this slide I show the first structure, passive structures that we have tested. This is a pad, so it's really needed in any monolithic circuit, since it is the input and output of any monolithic circuit, and we have measured and modeled. The model with lumped elements is mainly with a series capacitor with RC parallel circuit to model the change in frequency of the model. We have fabricated a test with 2 pads in open circuit, and this figure presents the measured and the lumped elements model, and we show a very good fitting. So the order of magnitude of the lumped elements model are 29 femtofarads for the main capacitor, and for the RC parallel we have a resistor of 238 ohms and 8.4 femtofarads. In the next slide we have shown the results of the second important test structure, that it's a transmission line with only 160 microns length and a width of 10 microns. And the lumped model we have used for this structure is a series RL circuit. And we saw in the Smith chart also a very good agreement between the model and the S parameters measured. The value of this line inductance is 86 picohenry, and the resistor is 0.355 ohms. So we go to the most difficult element of any passive library of monolithic circuits. That's the spiral inductor, especially for high frequencies like in millimeter wave band. So this is the only available inductor on the foundry of SiGe 25H3 technology, and the inductance is a tap one with 2 turns and a tap in the middle. As you can see in the figure on the right, you have a model that is more or less accurate up to 20 gigahertz, but it is not really accurate for higher frequencies, because this technology, as I explained before, it's not optimized for such frequencies. So we have introduced a series RL parallel lumped elements in the model supplied by the foundry, and we have obtained new model parameters for the lumped elements model. As the figure shows, the improved model is very accurate up to 45 gigahertz, giving very good results not only for the inductance but also for the key factor of the inductor. So we have designed a new inductor with similar dimensions as the previous one available in the foundry model, with 1 and 2 turns. In this slide I'm showing the results for 1 turn, so it's a similar model but adapted for a simple inductor without tap, and we have obtained also good results that has been shown in the Smith chart as parameters. We have good accuracy up to 45 gigahertz, and the main inductance of the model is 150 picohenries. So we can notice, comparing this value with the previous of the line, that they are of the same order of magnitude. So it's very important to have good models of the interconnection lines on the library for having a good design and good results between measurements and simulations. Here, to emphasize the precision of the model, we have the comparison between the derived lumped elements model for the real and imaginary part of the 2-port S parameters. Since the layout is symmetrical, of course S11 and S22 are the same, and S12 and S21 are also the same. Now in the next 2 slides we have the same results for the 2 turns, so showing that they are similar. Of course the inductance is about is higher, it's not 2 times higher, and the layout is asymmetrical. So S11 and S22 are not exactly the same, and S21 and S12 also. This is also to emphasize the accuracy of the model. In this slide we have the inductance of both spiral inductors, and we can see that the inductance, total inductance, is very constant on the millimeter wave band where we want to use it, so in the range of around 30 gigahertz.